environments, the typical velocity range for laminar flow is 0.36 to 0.45 meters per second. This range is considered optimal for controlling particle contamination without causing turbulence. The widely accepted industry standard is 0.45 meters per second, as it provides a good balance between removing particles and maintaining stable airflow.
Particle transport and removal. At 0.45 meters per second, the air velocity is high enough to continuously displace airborne particles and prevent them from settling onto surfaces. This is critical for maintaining the cleanliness class of the room, especially in ISO Class 5 or 6 cleanrooms. Minimizing turbulence. Higher velocities can cause turbulence, which disrupts the laminar flow and stirs up contaminants. A velocity of 0.45 meters per second provides a controlled, unidirectional flow that minimizes the chance of turbulence and ensures contaminants are efficiently swept out of the cleanroom. Compliance with ISO and GMP standards. Cleanrooms operating under ISO Class 5 or better, and GMP guidelines require the air velocity to remain in the range of 0.36 to 0.45 meters per second to ensure consistent performance and compliance with regulatory standards. Let's see the reactions at different air speeds with the smoke visualization we applied to the laminar flow unit. In this test, we will analyze the responses of optimal air velocity visualized with smoke. FFUs with 0.45 meter per second airflow ensure particles are continuously removed, protecting the wafers from contamination. Turbulence is minimized, preventing particle deposition on critical components. This air velocity is essential to maintain laminar flow throughout the cleanroom, ensuring that particles move in a controlled manner away from sensitive zones. Low air velocity in laminar flow can lead to several significant issues. It slows down particle transport, making it more difficult for clean air to carry particles away, which increases the risk of contamination. Additionally, reduced airflow can destabilize laminar conditions, resulting in turbulence that causes uncontrolled particle movement and deposition in critical areas. This decrease in velocity can also disrupt the uniform distribution of temperature and humidity, negatively impacting process efficiency. Furthermore, inadequate airflow diminishes the effectiveness of air dispersion, compromising overall cleanliness. Therefore, maintaining optimal air velocity is essential for effective laminar flow. When designing cleanroom systems such as FFUs or laminar flow units, the selected airflow velocity of 0.45 meters per second has a direct impact on the pressure drop across HEPA or ULPA filters. Higher airflow velocities necessitate increased fan power to overcome this resistance. To monitor filter performance, pressure monitoring devices, such as magnehelic gauges, are commonly installed to ensure that the filters operate within required parameters at this velocity. Additionally, the proper placement of FFUs and laminar flow units is essential to promote uniform air movement throughout the cleanroom, preventing dead zones where particles can accumulate. Maintaining pressure differentials between cleanrooms and adjacent spaces is also critical, supported by ensuring the appropriate laminar flow velocity. For a cleaner, safer, and eco-friendly working environments,